Alright, let's continue with the last part of this mini course in Elastohydrodynamic lubrication. My name is Roland Larsson. I'm at Luleå University of Technology in Sweden. This last final part of the course is about the influence of surface roughness on EHL, or maybe let's call it mixed lubrication. Actually, it's an attempt to discuss what is happening when the surface roughness start to play a role, which it does very often. Actually, this is so I actually used the title here: lubrication of real rough surfaces. And maybe this part of the course is the least clear one, and that's just because of this is still a research issue to fully understand how the roughness influences lubrication. As you may understand, surface roughness is a very important factor here in lubrication, since asperities are often the height of asperities are often in the same order of magnitude as the thickness of the film, or actually the asperities are higher than the film thickness very often. And so we will see here, for example, if you have a bump like this here, an asperity on the surface, it will definitely distort the pressure distribution completely and change or increase the pressure very much. What we have seen is that it depends on the shape of the asperity how big influence this have on the lubrication and the risk of failures, etc. But we can definitely say that there are good or bad roughness. It's not maybe good roughness, but it's less good and really bad roughness. And we can also see that sometimes the roughness is good in such a way that operating at lambda less than 1 is possible. So it's but we will try to compute a new lambda, a correct lambda for roughness. So when I discuss lambda, I refer to the Stribeck curve as usual, and this Stribeck curve is normally drawn for the undeformed roughness, but you will see that it's possible to change that a little bit. I made this picture some years ago to show or to at least think about how good the lubricant is, the reason why we lubricate. If you have a full film lubrication, the roughness on the surfaces, when one of the surfaces move relative to the other one, the pressure, the contact, or the fluid film pressure will vary up and down because of that, of course. But those variations are much smaller than what you can see in the boundary lubricate contact, where all load is carried by the contact spot themselves. And since the contact spots are pretty few, the contacts will be concentrated, and there will be sharp and high pressures in those points. And the mix is something in between, of course. So even if the film is thin, this is still creating a very good damping effect. So that's a little bit a picture of what the lubricant can do for you in a rough contact. The first paper, at least I am aware of, is the one by Patir and Cheng in the 70s. They tried to correct for the surface roughness, so they came up with a diagram of this type. Here you can see the film parameter down here, and they were able to model the effect of roughness and the roughness lay. So in this case, the roughness is along the direction of motion, longitudinal roughness, and in this case it's across this is the way it moves, sliding or rolling takes place, so roughness is transversal in this case. And in the between you have a isotropic roughness. So this case, this parameter gamma is bigger than 1. In this case, it's smaller than 1, and for the isotropic, it is 1. And they claim that if you lubricate, if your direction of motion is across or transversal the roughness like this, you can actually see beneficial effects. Or put like this, it is much better to move in this direction than in this direction. And they came up with a kind of correction factor to correct the lambda parameter. So if for small gamma, this correction factor could be over 2 if for small film parameters, while it can be less than 1 for small lambdas if you move in this direction. So by using that, you may improve your determination of the film parameter in this way. First of all, you compute the minimum film thickness from the expression for isothermal film thickness. You correct it by for temperature effect with a CT, and finally you correct it for the roughness effect by this factor, which you take from the diagram in the previous slide, and you divide it by the surface roughness height. And in this way, you probably get a better measure of what the number is of film parameter. And maybe these boundaries 1 and 3 for mixed and the full film lubrication they are pretty good boundary values then. Quite recently, in the past, say 10-20 years, people have also realized that the shape of the asperities and the wavelengths of the asperities play a big role. And actually, if you have very long wavelengths, or relatively long in comparison to the size of the contact, they are more or less completely squashed out inside the contact. That means that the RA will be more or less 0 then. So it really doesn't matter how thin the film is, there will always be a film parameter which is pretty large. On the other hand, if you have shorter wavelengths, these will not be deformed by the higher pressure, so some of them will still be in there, or even if it's even shorter, they will pass through the contact completely undeformed. Some researchers, for example, Ton Lubrecht and Kees Fenner, they were able to come up with a formula like this, or a diagram like this, showing the ratio between the deformed and the initial amplitudes. So if this ratio is 1, that means that the deformed asperity, well, it isn't deformed at all. So while if it's 0, it means that it's completely squashed out. So we really want to be down here, but as normally in engineering, we are probably up here instead. And this is a non-dimensional diagram, and this parameter is defined like this, where the lambda is the wavelength of the roughness. The S is a number describing the sliding. If S is 1, it's pure rolling, and if it's bigger than 1, it's sliding. Here you have the load, you have the Young's modulus, you have the radius, speed, viscosity, and alpha. So you can see how the different parameters influence this risk. But you can also see that if you have sufficiently long wavelengths, you will be up here, and your asperities are deformed. Another way to explain it was given by Bo Jakobsson, the formerly a professor here at Luleå University. And he saw it like this, that if an asperity enters the contact, it will capture some lubricant. It will create a high pressure also because this high pressure will keep the lubricant inside the contact, but since the pressure is highest here, it can't be any new lubricant brought into the contact really, so it will more and more grow as it passes through the contact. The asperity will grow out again from its deformed position, and if you are unlucky, it will grow as much as it enters the other surface and touches the other surface before it leaves the contact. You may compare that with buttering your bread with your butter knife. If you take some butter on the knife and move it over your sandwich, if you reach the end of the sandwich with butter on the knife, then you have a good lubrication. But if the butter finish before reaching the end of the sandwich, then you come into a contact problem. And you can play around with this back home by using the butter knife in different angles. You will see that the bigger the angle is, the bigger the risk for coming into contact with the bread. So this is just another picture of this effect. Here the asperity is in the inlet of the contact. It captures some oil here, the pressure increases, and it brings this oil with it during its motion here. But as it grows more and more, if you are unlucky, it has been growing so much that it touches the other surface before it leaves the contact. Jakobson came up with a kind of very simple relationship or criteria to avoid contact, and that is that the number of asperities multiplied by a sliding speed number, which is defined like this, which you may compute as the half width of the contact divided by the wavelength of the roughness multiplied by S. If this is less than 1, then you don't have any problem with roughness. This is a rule of thumb, but it's a very nice rule since it's so simple, easy to apply it. These are some pictures also from research here and at Leeds University. We made some tests with artificial pattern on the ball in the optical interferometry again. What you can see here is that if you have deep grooves between the flat parts here, we will empty the contact much faster than if you have shallow grooves. So next slide is maybe easier to understand. If you have deep grooves and you have some sliding, the captured oil here will as it moves, this is the same asperity but some milliseconds later, this captured oil will now move out and be drained into the deep grooves as this surface is moving faster, and finally it has been completely drained. While if you have more shallow grooves, this will not happen as easily, because then you will have some flow resistance in the grooves and pressure is formed also in the groove area. So that means that you should also be careful with how deep valleys you have in the surface roughness. Maybe valleys are more important than the peaks themselves. This is a picture I've taken from Anton van Beek's book. You can see more of that, by the way, at the www.tribologyabc.com if you want to see more there. This is the subsurface stress under a Hertzian contact. As you remember, the maximum effective stress is down in the material. If you add some roughness on this now, you see here that the maximum stress move closer to the surface, and that is increasing the risk for pitting and surface initiated pitting also, that you and maybe even plastic deformation at the surface. But then the big thing is that if you add some sliding as well, so you add some shear stress upon the surface, then you significantly increase the stress in the surface, and especially at the surface. Now you have a very much bigger risk of plastic deformation or surface initiated damage here. You can see here, note that this scale is now on 0.45 dimensionless units, while in this case it was only 0.28. This is another quite recent work. It's by Shu et al. At the Northwestern University in the US. They were able to model the rough surface contact as it is, the lubrication of a rough surface really, and they were able to model the lift-off speed here. So this curve shows how much. This curve shows the film parameter, and this curve shows the real area of contact, or the how much contact you have here. So in this case, when the degree of contact is 0, that means full film lubrication. So here, around here, full film lubrication occurs. And you can see here that the lambda parameter at that, when that happens, is around, it is around 2.5. So the Stribeck curve is pretty okay if we can trust this type of modeling. Some interesting results from experiments are shown in this picture. It's made at Imperial College in London, and here you again can see the effect of the slope of the surface, or the asperity slope. So they compared 3 surfaces, and they were able to measure the resistance of the contact over the contact. The more contact you have, the lower the resistance will be if you create a kind of electrical circuit of this system. So if you have very good contact between the chromium coating here and the steel ball, then you have much metal contact. So they measure the electrical in contact time. If that is high, that is much contact. So again, at low speeds, you have high electrical low resistance. But you can see here for the smooth surface, with the one with the smallest slope, you will start to see the lift off already here, and that goes down, and you reach full film somewhere here, while the surfaces with bigger slope have lift off later, and again even later for even bigger lift asperity slope. We have seen something similar ourselves when we have measured with 2 different surfaces. Here you can see the resistance directly, and this is a ground surface, 2 different lubricants, the base oil only, and a fully formulated with the additives. And what you can see here is that the resistance in the beginning is low. That's because this is before running in. But then when running in takes place, the resistance increases more and more, because of that the asperities are plastically deformed, and the film formation is better and better. You can also see here that the fully formulated gave us a bigger resistance, so we probably created both a tribofilm and a fluid film, which gave good insulation electrically. For the chemically deburred surface, which has a more smoother appearance, a lower slope, you don't see any big effect of the additives, so that you get approximately the same resistance for both surfaces, meaning that you probably don't have as much plastic deformation and need for the additives for this type of surface. So in the very beginning, in part 1, I asked which bearing can carry the highest load, and I can now say that both bearings can carry about the same load. And the reason to that is that this is under rolling motion while the journal bearing under sliding motion. And as you have seen here, sliding has a detrimental effect on the film formation and the risk of creating contact of the surface asperities. And you also saw that the stresses in the surface becomes bigger when you have rough surfaces in contact. And finally, some few words of about particles. We haven't really discussed this before, but of course particle is a big issue in EHL, and if it should work good or bad. Maybe the most important parameters and even more tricky to determine its influence. This picture shows kind of 1 micrometer big particle in a contact with only 0.1 micrometer, which is not at all unusual. And you can of course understand that this thick particle will make some indents in the surface and create some damage in the surface. Now remember the scales here. This particle is 1 micrometer in all directions, while this film thickness is 0.1 micrometer in this direction, but maybe 1 millimeter in this direction. So the particle will probably make an indent in the surfaces, but not over the whole contact, of course. So it's just a matter of how you draw the picture. But again, the size of the particle is important, and maybe even more important, the hardness of the particle. If the particle is harder than the surface, it will definitely create an indent in the surfaces. So that was the end of part 4 and the end of the mini course. I hope you have learned a little bit about how EHL works and the mechanisms of that, and also something about the challenges. Thank you very much.